Conditional expectation. Another way of computing the expectation of a variable is by using conditional expectations. The conditional expectation E of x conditioning on A is the expected value of x given that event A occurs. Accordingly, E of x conditioning on A is defined by replacing the absolute probabilities in the definition of E of x by probabilities conditional on the occurrence of A. In other words, E of x conditioning on A is equal to the summations of I times the probability of x equals to I conditioning on A, summing for all index I, where I ranges through all variables x takes with a positive probability, given that A occurs. We can then extend Theorem 15.15 to expectations as follows. Theorem 15.24, let x be a random variable, and let a1, a2, a3 until an be events in a sample space omega, so that a1 union a2 union a3 and so on union an is equal to omega, and ai intersect aj is not empty if I is not equal to j. Then the expectations of x is equal to the summations of E of x conditioning on A times the probability of ai, summing with index I starting from 1 to n. Proof. This follows immediately from Theorem 15.15. Just let C be the event x equals to j in that theorem. Multiply both sides by j and sum over all values of j taken by x with a positive probability. Example 15.25. We throw a die 3 times, provided that the first throw was at least 4. What is the expectation of the number of times a throw resulted in an even number? Solution. If the first throw was an even number, then the expected number of times we got an even result is 2, as it is 1 over the last 2 throws and is 1 over the first throw. If the first throw was an odd number, then this expectation is 1. Therefore, Theorem 15.24 implies that E of x is equal to the summations of E of x conditioning on ai times the probability of ai, summing with index I starting from 1 to 2, which is 2 over 3 to third times 2 plus 1 over 3 times 1, which is equal to 5 over 3. In this problem, it was very easy to compute the probabilities P of ai. The following problem is a little bit less obvious in that aspect. Example 15.26. Our football team wins each game with 3 over 4 probability. What is our expected value of wins in a 12-game season if we know that we won at least 3 of the first 4 games? Solution. We either won 3 games, event A1, or 4 games, event A2, out of the first 4 games. If we disregard the condition that we won at least 3 games out of the first 4, event B, then the probability of A1 is equals to 4 times 1 over 4 times 3 over 4 to the third, which is equals to 27 over 64. And the probability of A2 is equals to 3 over 4 to the fourth, which is equals to 81 over 256. That condition, however, leads us to the conditional probabilities. P of A1 conditional on B, which is equals to P of A1 intersect B divided by P of B, which is equals to 27 over 64 divided by 27 over 64 plus 81 over 256, which is equals to 4 over 7. And P of A2 conditioning on B is equals to P of A2 intersect B over P of B, which is equals to 3 over 7. In this problem, we assume that B occurred. That is, B is our sample space. To emphasize this, we will write PB of AI instead of P of AI conditioning on B. We denote the expectations accordingly. In the last 8 games of the season, the expected number of our wins is certainly 8 times 3 over 4, which is equal to 6 by theorem 15.18. Therefore, denoting the number of our wins by x, theorem 15.24 shows that EB of x is equal to EB of x conditioning on A1 times PB of A1 plus EB of x conditioning on A2 times PB of A2, which is equal to 9 times 4 over 7 plus 10 times 3 over 7, which is equal to 9 and 3 over 7. We see that this expectation is larger than 9, the expectation without the condition that we won at least 3 of the first 4 games. This is because that condition allowed us to win all 4 of these games, which is better than our general performance. Note, this chapter was not as much on probability theory itself as on the application of probability in combinatorics. While there are plenty of textbooks on probability theory itself, there are not as many on discrete probability, that is, when omega is finite. A very accessible introductory book in that field is Discrete Probability by Hugh Gordon. As far as the probabilistic method in a combinatorics goes, the classic is the probabilistic method by Alon and Spencer.